Okay, so this is our second video on Chapter 3 material. In the last video we introduced um, the notion of an absolute or global maximum value, and we stated this extreme value theorem, which gives us conditions under which we can be guaranteed that these absolute max and min values exist. In this video we're going to look at what are called either local or relative extreme values. So these are values which maybe don't give you the largest value on the entire domain for your function, but they might give you the largest value on a piece of the domain. So here's the definition. You'll notice it's pretty similar to the one we gave, except this time I'm going to specify a domain, D, and a local or relative max is now going to be, well, when do we attain a local maximum? So at a point C, or maybe we're being a little bit lazy here. Maybe we want to give the entire point C and f of C. So when do we get that local max? We get that local max value if you can find an interval around this point C so that f of C is the biggest value on that interval. So maybe not on all of D, but it's the biggest value at least on this interval I. Similarly, for the local minimum, we can say that you have a local minimum value if it's the biggest value you see on some interval. So here's one particular example. F of x equals x cubed minus 3x. Now I've plotted this one on GeoGebra so you can see what it looks like. Here it is. Okay. Now notice that if I don't restrict the domain at all, there's clearly no absolute maximum or minimum value, right? Because we can see that we're going to go off towards infinity in this direction. We're going to go off to minus infinity in the other direction, and so we're not interested in that. What we're interested in is a couple of these points that we have, right? So we see that there's this point right here at the very top. That is a local maximum, right? Because if I were only considering the y values for my function with x running between, let's say, maybe from minus 2 to 0, if I was only considering those y values, well, then that would be the biggest y value I see on that interval. Similarly, down here, oops, I want to point again. If I took that point there, that would be a relative minimum or a local minimum, because if I was only considering x values between, let's say, 0 and 2, that's the smallest y value that I see. It's not the smallest y value that I see globally, because we have this part of the graph over here where we're, when y is less than about, or so when x is less than about minus 2, we start getting y values that are smaller than that y value that we see over there, right? That y equals minus 2. But at least, if I kind of stick in this valley, that's the smallest value that I see. If I kind of stick near the top of this mountain, that's the biggest value I see. That's the idea of the local maximum or local minimum, right? It's not going to be the biggest value you see over the entire graph, but it's the biggest value that you see over a piece of the graph. So this, if we kind of look at those points, right, we have a local max. This guy here has a local max. We're just getting this from the graph, right? The local max is going to be at minus 1 and 2. Notice that if I put x equals minus 1 into my function, I do get y equals 2 out, right? F of minus 1 is equal to 2. And there's a local min at 1 and minus 2. Those are not the global max and min values, but they are local. One thing you might note, if we calculate the derivative, and you probably know where this is headed, you've seen enough examples by now, f prime of x, I get 3x squared minus 3 for the derivative. And if I factor, that's 3 times x squared minus 1. Well, that's 3 times x minus 1 times x plus 1, right? And so notice that f prime of 1 is 0, and so is f prime of minus 1. Right? So these points where our local max and our local min occur, those are exactly the places where the derivative happens to be 0. These places where the derivative is 0, they have a name. These are called critical points. Right? So a critical point for a function is any point where the derivative is 0 or where the derivative fails to exist. Although in this second case here, the possibility where the derivative does not exist, we're not interested in points where the derivative doesn't exist because the function isn't defined there. So we do want to make sure that this point is in the domain, right? So if we're looking at something like, say, that 1 over x, y equals 1 over x, well, it's true that when we take the derivative, it's not defined at 0, but the function itself wasn't defined at 0 either. So we're not interested in points like that. We're not interested in these points that correspond, let's say, to vertical asymptotes. We're interested in points that are in the domain where the derivative is undefined. So here are a couple of examples. Let's say we want to find the critical points for this function f of x. So we're looking for places where the derivative is either 0 or undefined. So, well, the first thing we need is the derivative. 4x cubed minus 16x, using the power rule. If we factor 4x times x squared minus 4, so we get 4x times x minus 2 times x plus 2. So we can see that f prime of c is 0 for c equal to 0, 2, or minus 2, and obviously there are no points where the function is undefined. So those 3 points there are our critical points. Now what about g? If I calculate g prime, I get 1 minus 3 times, so we use the power rule here, 1/3 x to the minus 2/3. Okay, so that's 1 minus, so 3's cancel, x to the minus 2/3. So 1 minus, let's deal with that negative exponent. That's 1 minus x to the 2/3. And if I put things over a common denominator, this is x to the 2/3 minus 1 over x to the 2/3. So now we can see that g prime of x equals 0 if x to the 2/3 is equal to 1, and that is if and only if x is equal to either plus or minus 1. Okay, because of that 2, right? 2/3 means we square it and then we take the cube root, or if you like, you take the cube root and then you square it. Either way, both plus and minus 1, they both work. And also notice that g prime is undefined if, well, x to the 2/3 equals 0, so if x equals 0, right? And that is also a critical point because 0 is in the domain for my original function, right? G of 0 is defined. G of 0 happens to be equal to 0. And if we plot this, let me see if we can get that plotted to see what it looks like. Okay, so let's get a new file going here, and let's say I go with g of x equals x minus 3. It's not going to like this, is it? Let's go to a proper keyboard. Okay, g of x equals x minus 3x to the 1 over 3. Okay. There it is. There's our function, and you'll notice that those critical points, right, at plus and minus 1, we can see those here, right? There's one. There's the other one. Those correspond to a max and a min. What about that critical point at 0? Well, you can notice that what happens as you pass through 0 is the slope of the tangent line becomes infinite, right? So the derivative is undefined there because the slope is approaching infinity, right, which is not a value that we can consider, and so we have a vertical tangent line at that point. So this is one of the situations where a derivative can fail to be undefined. You might have a vertical tangent, and that's why the derivative is undefined. You can also end up in situations like if you considered simply something like y equals x to the 2/3. If you were to graph something like this, you get this sort of, like a child seagull kind of shape, where you have that cusp, you have that point on the graph, right? So the derivative is undefined at that point, even though that point is in the domain. So that is a critical point, right? And notice that that is also a relative minimum for this function. And so we're interested in finding these minimum values, and that's why we want to include the possibility that our derivative might be undefined at a relative max or a relative min. Okay, so here's a theorem. This is usually attributed to Fermat. It's not Fermat's last theorem. It's not his famous theorem. This is another theorem. But Fermat's theorem says that if our function has a local extremum, so either a local minimum or a local maximum at some point, then the x-coordinate of that point has to be a critical point for your function, right? I'm not going to get into the proof here. The details are in the textbook. If you want to see the proof, you can dig it out of the definition of the derivative. But basically, what this theorem says, this sort of moral of the story, if you like, is to find maximum and minimum values we should look for critical points. Okay. So the critical points are going to tell us where we might find those max and min values, at least those local max and min values. In the next video, we'll see how to solve the problem of finding absolute max and min values.